Hello, everyone. Welcome to this pre-recorded video. A quick announcement. If you're watching this on Friday or the weekend, we will be back in seat on Monday. My quarantine will be up, and I'm looking forward to seeing all your half faces again under masks. I have to admit, I'm a super introverted person, but spending too much time alone, it gets a little depressing. So it'll be nice to see everyone again. All right, with that, let's get into material. We're looking at 3.1 here. And I should say, this is going to start kind of a big section of the course. We started with first order differential equations, and we saw that there were various techniques one could use to solve first order differential equations of certain types. You could plot a slope field or direction field, and then look at solutions traveling through that slope field. You could analytically approach differential equations if they had certain forms. You could use corresponding techniques to actually come up with the solution formula. But that was all in the first order realm, and there were a variety of different techniques and different types first order. Now what we'll be doing is looking at second order or higher in general, and in particular, looking at linear differential equations. And we'll start with linear differential equations of a certain type. Now, when we looked at first order differential equations, there was a notion of linear. In fact, if I just focus on this part, that's obviously first order, and it fits the form we saw before, where maybe before we would have put this as like a P of X, and this is a Q of X. Now we'll call them A with certain subscripts. But linear, unlike things such as separable, I'm trying to think of others, and some other first order types that are coming to mind, linear does extend beyond first order, and it can be really any positive integer order. So you could have a 10th order linear differential equation and so on. The general form is this, and it's highlighted in color to try to make it more clear. You have functions of just the independent variable, which in this case will have bx. And then you have the dependent variable, and you have just derivatives of the dependent variable. So you have the 0th derivative, that's why it's a sub 0. You have the first derivative, that's why it's a sub 1. You have the n minus 1 derivative, just why it's a n minus 1. You have the nth derivative, which is why we have the subscript of n. So these functions out front can be anything in terms of the independent variable. With the dependent variable, all you can do is take successive orders, or I should say successive derivatives of that dependent variable. So we have 0th order, first order, and so on. And as long as you can write it this way, we would call it a linear differential equation. Now, to start with, we're going to simplify this down in two ways. The first way is we're going to assume that this thing here is going to be equal to 0. When we have a linear differential equation with this a of x function being identically equal to 0, that's what we call a homogeneous linear differential equation. We'll further simplify by, instead of letting these coefficient functions be anything, be, let's say, cosine of x or e to the x or something like this, let's have them be constant. So the homogeneous is the a of x function being 0, or as we set it up like so, the right side is equal to 0. That's homogeneous. The constant coefficients, as the name implies, we're going to take the coefficient functions and have those be constants. So now let's drop the of x notation to denote that it doesn't actually depend on x, it's just a constant. And if we rewrite those as, let's say, just a sub n, where there's no x, where we're not just suppressing the x and it's actually there, we really mean constants. So each one of these, a sub 0, a sub 1, etc., these are all constants. Now, as I may have mentioned, this will be kind of our base. We'll look at how to solve these types of differential equations. And then we'll, as kind of a next step after that, we'll let this no longer be strictly homogeneous. We'll let a of x be something that's not 0. We'll see how to solve from there. And then we may or may not, I haven't looked quite that far ahead, look at some cases where we have non-constant coefficients here. But the good baseline is the constant coefficient and homogeneous. Now, with that said, there's a really nice solution method. It's an analytic solution method. So it's worth noting this is analytic. And in this course, we've been using analytic to mean there's some method you can go about to find a solution formula. With the geometric method, as kind of a reminder, you might plot a slope field, and then you're not actually finding a solution like function or formula. What you're doing is you're finding graphically curves that, let's say, pass through this thing. But you don't have like something such as f of x is equal to blah, 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 or y is equal to blah, blah, blah. You don't have that. You can just graphically see what it looks like. So in some sense, it can be kind of easy to see what the solutions are in the geometric case, but it's then hard to be exact if you want to know, okay, what is this value precisely when, x is equal to whatever, what's that y value? So it's quicker, but less exact. The analytic is in many ways kind of the best, but it's sort of the hardest. It requires the greatest variety of different techniques, and it usually just kind of requires a lot of algebraic work. But in the case of the constant coefficient, linear, homogeneous equation that would look like this. Notice again, we have the 0th derivative, the first derivative, et cetera, up to the n-1 derivative, up to the nth derivative. Oh, and actually I should change this. I had a there, but that should really be 0 for it to be homogeneous. Apologies for the typo there. And I don't know why that 0 is bothering me. There we go, a little nicer. All the coefficients then are equal to 0. Or sorry, all the coefficients are constants. If we have this, the characteristic polynomial, which we'll denote as P of R, just for like P for polynomial, and in the variable R, you can change it to a different variable. R is not important in particular. I'm not sure if the book uses it. It's one I'm in the habit of using from certainly other differential equations courses, but either way, it's a polynomial in some variable. And if we look at the two kind of above and below each other, that is the differential equation, the characteristic polynomial, hopefully I've set it up to make it clear that there's a really direct and obvious correlation between the two, namely the coefficients in front of the terms in the polynomial should be the same as the coefficients in front of the successive derivatives in the differential equation. So you take the exact same coefficients. When you have the nth derivative, you have the nth degree, r to the n. When you have the n-1 derivative, you have r to the n-1, and so on. So whatever the order is up here, that's what power you're taking r to. And then this is like the 0th derivative. So it's like we took r to the 0, which of course is 1. So once you have this set up in the right form, it's really easy. Again, once you're comfortable with it, I mean, there's a lot of information to absorb. So don't worry if it's not immediately obvious why we care about this or should do it. But once you're kind of comfortable with it, it's really quick. Let me say that, really quick to write down the characteristic polynomial. Now, excuse me. Now, why are we doing that? Like, who cares? Well, what we're going to do is we're going to take that characteristic polynomial, and then we're going to find the roots or the zeros of it. And now this is something that maybe, well, almost surely is not like in the forefront of your mind or like probably immediately accessible because we sort of don't name it a ton. Maybe we don't even use it that much either, but it's, as the name implies, a really important result in algebra. And it essentially says that if you have any nth degree polynomial, and maybe I should even be a little more exact, polynomial with real coefficients, that is real numbers for coefficients, this has exactly organizing, has exactly n complex roots. So even if your polynomial doesn't have any imaginary parts, doesn't have any I, it's just real numbers for the coefficients. Even if your polynomial is in real coefficients, you can guarantee there's going to be n roots, you know, along with multiplicity or accounting for multiplicity. But the roots themselves may not necessarily be strictly real. They're in general complex. For example, if we take, let's say, the polynomial p of r is equal to r squared plus 1. Now, this has no real roots. There's no real number we can plug in for r to have this expression then be equal to 0. But there are complex roots. Namely, if we take p of I or we take p of negative I, both of those happen to be equal to 0. And that's just a really simple little example to maybe ground the fundamental theorem of algebra a little bit more. Now, that's really nice, actually, that it's up to multiplicity. We get this number of roots because we'll use each one of those roots in constructing the solution formula. So it just so happens that when we construct the characteristic polynomial, and then we look at the roots, by the fundamental theorem of algebra, we're going to get enough of them. It's going to be nth degree polynomial, nth order derivative, n complex roots. That's a good thing. Then finally, we create our solution formula based on whatever the roots are. Now, at the base level, if you have a real root and it's not repeated, so notice down here I've got some space for repetition. So when we look at the roots in the real and complex conjugate pair case, we're assuming that they don't repeat, that they have multiplicity 1, as it were. So if your root is, let's say, r, then you would get a solution term that is e to the rt. Okay, that seems good. If you have a complex conjugate pair, and whenever you have a complex number, where by complex number I mean here that the imaginary part is non-zero. So when you have a number something plus some non-zero number times I, whenever you have a complex number, you'll also have its conjugate. So they'll always come in pairs. You'll never have, for example, just 2 plus 3i. you would never have just that as a root. You would also have to have 2 minus 3i. They just always come together. It's not actually, I'm not sure if that's difficult to show or not for a general polynomial. Maybe not. Maybe that wouldn't be difficult to show, but it happens to be true. Now, along with the fact that you have a complex conjugate pair, you also get 2 terms. Essentially, for every single root, including multiplicity, you get 1 solution term. When we have a pair of complex numbers here, and they're complex conjugates, meaning they're the same, except the sign is different between them. When you have that, you also get a pair of terms. So you've got a pair of roots, you get a pair of terms. They look like this. The real part is similar to the real root up here. So notice some similarity here. R is a real number. Alpha is the real part of the complex numbers. And we get this same kind of, how do I want to say it? Same kind of expression. Real part is alpha, we get e to the alpha t. Along with that, to account for the beta I, or negative beta I, we also have cosine and sine. Each one of these is a separate term, as we'll see. And again, we have no repetition here. We'll address repetition soon. Okay, first thing, find the general solution of this differential equation. The first step is to find the characteristic polynomial. So we do that. Let's see. Let me copy this, shrink it, highlight coefficients. This may be very obvious to you so far, and if so, that's great. But just in case it's not, or at least to make it have there be less confusion, I'm going to zoom in the future. Let's say we have 2 and then minus 3. So plus 2 and plus negative 3, if you will. All right. Now, when we do our characteristic polynomial, and actually I'm going to get rid of that 0, move it over a bit. We have P of R is equal to 1 times R squared, because it's the second order. So we get R squared. Then we get plus 2 times R. It's first order. So it's R to the 1. And then finally, we've got minus 3, just period. We can think of that, if we like, as R to the 0. If you like, if it's, I don't know, more helpful, at least to start with, to kind of see how these really line up. But long story short, we'll get R squared plus 2R minus 3. Now, with that characteristic polynomial, what we do is we find its roots, or find the zeros. It's the same thing we're trying to find. So to find the roots, we take this and we set it equal to 0. We want to find the R values such that when we substitute them in to the polynomial, or evaluate the polynomial at those values, we get 0. This is a second order polynomial, or second degree polynomial. We can use the quadratic formula. Actually, let me move that here. Let's see, yeah. And then let's put that over here. So we get that R is equal to negative B, in this case, that's 2, divided by 2 times A, which is 2 times 1, A being 1 here, plus or minus 1 over 2A, which is 1 over 2 times 1, Square root of b squared, which is 4, minus 4a, which is 1, times c, which is negative 3. Okay, sorry for the silence. I was thinking that we would want to come up with complex roots, but no, we will have real roots in this case. So I was thrown off by the negative giving us a positive. No, that's fine. What we get is negative 1 plus or minus 1/2. I was getting a little too excited for the complex conjugate pair. I was just pumped. I like complex numbers. They're super cool. We can simplify this. We can factor out the 4, which becomes 2, leaving us with square root 1 minus, factored out the 4, so 1 plus 3, giving us negative 1 plus or minus 2. That was a little bit of overkill, but I kind of went there instinctively because in general, you can't assume that this is going to factor nicely. If you can find them quickly, great, then factor it. Might save you, it'll probably save you some time as opposed to going through this. But when you've got second order, you can always guarantee that this will give you roots for sure. So let's see, what do we get? We get negative 1 minus 2, which is minus 3. And then we get what am I trying to say? 1. Though we should be able to see that this is, yeah, no, that's good. Okay, we get 2 roots using the quadratic formula or factoring. So we get r as negative 3 and 1. Now taken individually, let's say negative 3. Negative 3 is not repeated. We don't see it ever again. It has multiplicity 1. So because of that, because of this r is equal to negative 3, we're going to get a solution term that is e to the negative 3 times, I guess we haven't specified an independent variable. Let's do e to the negative 3x. So that comes from having one of these roots here. I'll maybe put this in cyan. Then another term is e to the 1 times x. Maybe I'll put that in another color. Put that in, how about yellow? We get 2 terms. Now that's not the whole solution. There's a little bit more to it, but once you have the terms, there's not too much more to do. Let me do what? Let me shrink some of this work so that we can have a little bit more room now that we've done this. Good. And we just need to give ourselves room to be able to actually write what the solution formula is. So what it will end up being is y is equal to c1 e to the negative 3x plus c2 e to the x. And that's it. You might further ask if there are any singular solutions. And that's something we don't talk about enough. Let me rewrite that. When it gets near the bottom, it can be hard to write. So, or hard to write nicely, singular solutions. So these are things of the form y is equal to some constant where that itself is a solution. So if we were to take y is equal to k, where k is a constant, and we were to substitute that into the differential equation, well, y prime is 0, because k is constant. Y double prime is certainly 0. So all we would get substituting it into the differential equation would be -3 times k is equal to 0. And that, of course, is only going to be true when k is equal to 0. So there is a singular solution, namely y is equal to 0. I think I've seen some texts only call this the general solution, but when I say general solution, what I will tend to mean is all of this. On an exam, if there is only like one box for entry and it says find the general solution, then what you would want to do is input this one. But when I say general solution, I will, in general, mean kind of every solution formula we could come up with. Okay, good. Now, as I was kind of expecting with this last one, let's have a case here where we will have complex roots. So the first step, maybe not find, maybe we'll say write characteristic polynomial. That, of course, is going to be P of R is equal to R squared plus 2R plus 3. So we have 1 here, second order, so we get squared, 2 here, and then 3, so we get 3 here. Next, we'll find the roots. So we want 0 to be equal to R squared plus 2R plus 3. Right now, we shouldn't be able to factor this nicely over real numbers. So we'll definitely need the quadratic formula. I feel silly in the last one that I didn't see that it factored right away. Silly me. Quadratic formula. R is going to be equal to, negative b, which is 2, over 2 times a, so that's divided by 2, plus or minus 1 over 2a, times the square root of 4 minus 4, because that's 2 squared, minus 4 times 1, which is a, times c, which is 3. And that will give us -1 plus or minus, we can factor out the 4 in both of these. And when we pull that out of the square root, it becomes 2. 2 divided by 2 is 1. That leaves us with 1 minus 3. So we get -1 plus or minus square root of 2 times I. Now we have something that's strictly complex. It cannot be considered to be a real number. Now what we have is a pair that is not repeated. In particular, we have R is equal to -1 plus square root 2i. Then we have R is equal to -1 minus square root 2i. So here's the complex conjugate pair. They are the same with their coefficients with the exception of the sign change for the imaginary part. Now that we have these, and I'm going to delete this because since it's a video, you can always go back and check it. We've got these two roots. Now for each one, we're going to get a solution term. So we assemble the solution. For each root, we get a term. The first term that we'll get is e to the, actually, let me color this. Oops. I think it's helpful to have color in this case. So we'll do the real part in this magenta and the imaginary part in this cyan color. So we get e to the negative. I'm going to use t here. I'm going to use a different independent variable just for something new. Then we're going to have cosine square root, oops, in cyan, square root 2 times t. There's one term. And let me sort of push this off to the side and just indicate what we're finding are terms, things that will be put together to get the solution formula. Then we also have, again, oops, e to the negative t times sine of square root 2 times t. We had two roots, pair, complex conjugate pair, and then we get two terms from it. When we assemble the general solution formula, or part of the general solution, we just take these and we combine them as this sort of linear combination, where C1 and C2 are what we call parameters. In the first order case, we would have one parameter, but now in the second order case, we have two parameters. Whatever the order is in general, that should be the number of parameters you have. Now, if we want to actually find the parameters, we need more information. If I flip back to the previous question here, we did not have any additional information. So all we could do is get down to this case where we had two parameters. Now we do have additional information. Whatever order your differential equation is, you need that number of pieces of information to be able to find all of the parameters. Since it's second order, we want two pieces of information. Now, once we have that, we can try to find C1 and C2. So let me take this here. And actually, I'm going to copy a lot of this structure, find the exact blah, 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 blah. We've gone through all this. Now we're to the point where we know what the solution formula, the non-singular solution formula should look like. There we go. Now all that's left is actually finding what is the C1, C2. So there we go. We'll now use the information. I kind of want to have more room here. So let me shrink this a bit, resize, just to hopefully give us enough room to work. All right. First, we use y of 0 is equal to 0. And I'm even going to shift this over so it's kind of nicely organized. That we add the solution formula or a solution formula. Now we're going to use this information. We substitute that in, we get 0 is equal to C1 e to the 0 times cosine of 0, which is 1. So we get 1 times 1. Then we get plus C2 times 1. And then sine of 0 is 0. So this simplifies down to C1 is equal to 0. Now what we can say, based on that, is that y is equal to C2 e to the negative t sine of square root of t, a square root of 2t. Now, it won't always be the case that one of your parameters is 0, but it can be. Nothing's saying it can't. And now let's use the second piece of information, which is that y prime of 0 is equal to 4. So y prime, in this case, going off of what we have here, because we already know C1 is 0, y prime of t is going to be equal to negative C2 e to the negative t sine square root of 2t plus, is that right? Yep, plus square root of 2 C2 e to the negative t cosine square root of 2t. Now we substitute the information that y prime of 0 is 4. We get negative C2 e to the 0, which is 1, sine of 0 is 0 plus square root of 2 c2, 1 times 1. So we get that 4 is equal to square root of 2 c2, and then hence 4 divided by root 2 is equal to c2. And sometimes we like to have the square roots only be in the numerator, so you might do what's called rationalize. If we multiply the top and bottom of the expression 4 divided by square root of 2, what we'll end up with is 4, actually we're going to end up with 4 square root of 2 divided by 2, which is of course equal to 2 root 2. So I'm going to say 2 root 2. It's not strictly necessary. It's not a different number. It's just some people are in the mathematical habit of making sure, if possible, to not have radicals like square root or cube root in the denominator. But at any rate, we get C2 here. Now we can go back, and since we now know C1 and C2, we can just substitute. So I'm going to zoom in a little bit, just so when I erase, I don't erase too much. And what we get is, well, I guess 0. And for C2, like we said, 2 root 2. And now we have our exact solution. Okay, this was all without repetition of roots. Actually, yeah, let's do one more example here. What's different here is this is higher than second order. Namely, it's third order. And the reason I have this example here is to show what happens when you have both complex and real roots together. So the first thing we'll do is find the characteristic polynomial, which is P of r equal to r cubed plus 4r squared plus r plus 4. We might be able to see how that factors by noting there's coefficients 1, 4, and then 1, 4. So we can take r squared times r plus 4 plus r plus 4 is equal to r plus 4 times r squared plus 1. And if you like, you can think of it like this. Actually, let me structure it a little bit like so. So if the r squared is on the left here, we can think of there being a 1 on the left here. And then when we factor out the r plus 4, let's put that to the right because it's on the right side in each of these. Then we get r squared plus 1. Now there's one root clearly already, namely negative 4. That's a real number, excuse me. And then it's actually also not too hard to see what the roots are of this. They're not real numbers, they're complex. So find the roots. Those will be r is equal to negative 4. Then we have r is equal to negative I, and then r is equal to I. So you have one distinct real root, and then you have a complex conjugate pair. No repetition. No root is repeated. Actually, let me organize it like this. Because then when we look at the solution formula, so symbol solution, for each root, we're going to get a term. And I want there to be room here. So we get terms. For the distinct real roots, we get e to the whatever the root is times whatever your independent variable is. I'll go back to x for the moment to mix it up. Then for a complex conjugate pair, it's not like either one is really associated with a particular root, like cosine or sine. Actually, this is going to be e to the 0 times x times because the real part is 0, times cosine of 1 times x. And this is e to the 0x times sine of 1 times x. And let me put a little bit more room here. And that may be confusing where this is coming from. So let me rewrite the roots like this. We can think of the real part being 0. That's why I'm putting a 0 here. And then we can think of the coefficient in front of that I just being 1. Let me space that a bit. So it's negative 1 times I plus 1 times I. And that 1 is what goes here. Of course, this simplifies quite a bit. This is just cosine of x. This is just sine of x. But so that you can see the structure of how the complex number gets converted into these terms. And like I was starting to say, it's not like the, excuse me, it's not like the complex number with the negative coefficient goes with cosine and the positive one goes with sine. It's not really like that. These could be switched around. The thing is, it doesn't really matter because they always come in pairs. So once you have the pair of these, okay, we have both of the signs, the positive sign and the negative sign, because we have the conjugate pair. And then so too, just like the conjugate pairs go together in the roots, so too did these solution terms. So when you're initially generating the solution, if you have a sine, you'll also have a cosine. And then finally assembling all that, well, there's not too much to it. We just take y to be c1 e to the negative 4x, the first term, plus c2, it simplifies just down to sine of x. And then plus c3 simplifies down to cosine of x. Oh, I realize I had a typo back up here. I apologize for that. I did not have a y here, and there definitely should be. So I apologize. I was thinking about polynomial, I think, when I wrote that in. Just wrote a 4, but there should have been a y there. And now I want to check and make sure I didn't. Yeah, okay. The other one was good. So my apologies on that. That was a typo mistake I made. Bad Jake. Very bad. Hopefully that didn't cause any confusion. And if it did, feel free to yell at me. Now, with that, as I started to stress before, we didn't have any repetition of roots. Now let's see what happens when you do have repeated roots. The general idea is somewhat straightforward, though it may not seem, it may not be obvious why we're doing this. When we talk about linear independence of solutions, that's where this maybe will start to make more sense. But just kind of know for now that this is how we deal with repeated roots. So if a root is repeated, we do what I'm calling scaling. And what that means is if we had r, a solution term would be e to the rt. If we had r again, well, there would be something redundant about just writing e to the rt again. So what we do to get a term that's quote unquote different is we do this, what I'm calling scaling for now. We multiply by the independent variable just in front. And we can keep doing this. So if a single root is repeated like 5 times, we can just keep scaling up. The one after this would be t squared, which we'll see in a second, and then t cubed and so on. And it's exactly the same for the complex conjugate roots. Remember, when we have one strictly complex number, we're always, as a root of a polynomial, we will also have its complex conjugate, buddy. Then that gives us 2 terms. It gives us e to the alpha t times cosine beta t and so on with sine. If we repeat this pair of complex roots again, so we have the pair here and here, and we again have the pair, which is totally fine. When would that happen? Well, r squared plus 1 squared. That's a polynomial, and its roots are negative I and positive I, and then it does the same pair again. So this would be a really quick example where we have a complex conjugate pair repeated. It doesn't happen too often because you would need at least a fourth degree polynomial and fourth order or higher order differential equation. But just to give you the idea that there's nothing really special between the real roots and the complex root pairs. Whenever you have repetition, you scale. And that is simply it. All right, with that, let's, well, actually, let's say a little more. A kind of point I was mentioning before is if you have a repeated real root or repeated complex pair, it doesn't matter how many times you repeat it. How we deal with generating new terms is we just keep scaling. So you just keep multiplying by the independent variable. So take this one times t, take this one, multiply that by t, which gives you t squared, and so on. And it's the same with the complex pairs. You've got one pair, you get your e cosine, e sine pair of terms. You got another pair of roots. You just multiply each one by t to get another pair of terms. If somehow you had at least a sixth order differential equation and you get 3, or you get the pair repeated 3 times, then you would just multiply each one by then t squared to get new terms, and so on. So if I flip back, there's no difference. You just keep scaling these up. T squared, t cubed. You just keep scaling it up. T squared, t cubed, and so on. Okay, with that, let's have some examples where we repeat roots. The characteristic polynomial is going to be P of r is equal to r squared minus 2r plus 1. This, of course, factors as r minus 1 squared. And now when we look at the roots, we get r 2 times, or I'm sorry, we get 1 2 times. Sometimes this is written as multiplicity greater than 1, like multiplicity 2. How I like to write it is to literally see each case. If you want to have it more compact, you might do this, or if you want to fit it all in line. But the way I like to do it is to actually see each one that we have. That kind of reminds me how many terms we should have and how I need to address each root to get each term. Now that we have all the roots, and we do, it's second degree polynomial. We've got 2 roots with multiplicity. And actually, I should take a step back. Why do we say it as multiplicity 2? Well, if we go back here, notice we have r minus 1 and r minus 1. So each of these factors contributes a root. So we get a 1 from this one, and we get a 1 from this one. That's where the multiplicity 2 comes from. Now, with that, we can assemble the solution. One term is going to be e to the 1 times, let's say, t. Now, if we just did e to the t again, kind of naively, for the second one, we will not have added anything new. If we were, so this is not what we want to do, but if we were, actually, let me put a visual warning. This is not correct. Just, how do I want to say it? Just motivation. Let me say it that way. We're trying to motivate why we would do this multiply by t. If we took y is equal to c1 e to the t plus C2 e to the t. Well, there's an e to the t factor common in both of these. So if we were to try to simplify, we could, and we get C1 plus C2 e to the t, which may seem like, okay, who cares? Well, C1 is just a constant. C2 is just a constant. If you add them up, it's just a constant. So this would really be C3 e to the t. And now we have a problem because our solution, our general solution formula that's non-singular, has only one term with a parameter, I should say, because that'll, when we get to non-homogeneous equations, there will be more than what I'm about to say here. But for linear homogeneous differential equations, constant coefficient, the order should dictate how many terms there are. And if we have second order, we should have two distinct terms, or what we'll call linearly independent terms. But we see here, there's only one term. So there's a problem there. So this is maybe some motivation why you would want to take and multiply this by t, do a little cleaner t. Now, when we, actually I can keep a lot of this. Now, when we write the general solution formula, first I should say C2, t, e to the t. Now notice we cannot combine these two anymore. I mean, you could if you wanted simplified in the sense of C1 plus C2 t e to the t, but these are not like terms here, so we can't combine them to get down to a single term, if you will. There still is in essence two terms. I like to, you can do it however you like. I like to leave it like this, where it's really clear that we have these two distinct terms. Okay, so all we really did was when we were coming up with new terms, if there was repetition, then we would do this scaling. All right, good. Now, whoops, I should erase this because now it is correct, and just re-highlight that this is the solution we want. Finally, without going through all the work, but in a similar way to what we saw before, there is a singular solution, and it's just y is equal to 0. All right, next one. Now we have, excuse me, fourth order, but that's fine. As long as it's linear constant coefficient homogeneous, we can use this characteristic polynomial method. The characteristic polynomial is going to be r to the fourth plus r squared, plus 2r squared plus 1. This should factor as, let me factor it over here, r squared plus 1 squared. Do I believe that? Yes. Which is r squared plus 1 times r squared plus 1. Now, from each of these, we get a pair of roots, strictly complex. Actually, I guess we might even say imaginary because they don't have real parts. So find roots. We get r is equal to negative I, r is equal to I. There's one pair. Actually, let me put them side by side. And then we get r is equal to negative I and r is equal to I again. Each one of these factors gives us the pair here. Now we'll assemble the solution. And what we get is for each root should give us a term. When we have complex conjugate pairs, we get two terms at once. So our terms should be e to the 0 times cosine of 1 times, do I have an independent variable? No, we'll use x. Then we have sine of x Now, because we're repeating this complex conjugate pair, we'll take the same terms and we'll quote unquote scale them. And now we have, for our 4 roots, we have 4 terms. To put this all together, we don't do anything different. We just take C1 times our first, yeah, got you, cosine, times our first term that we came up with, plus C2 times our second term, plus T, or C3, T cosine of X. I'm going to fill that T in a second, plus C4, fill the T in sine of X. And that's it. We have a 4th order linear constant coefficient homogeneous differential equation. That should give us 4, I'll just say for now, distinct or distinct enough terms. All right, good. Well, I think that'll do it for this lesson. It went a little long, but hopefully it was covered in a way that was very clear. As always, let me know if you have questions, and y'all have a good day.